Is everyone ready? Yeah. Okay, so let's start with the first resistor model. Okay. Let me throw away the beams. You can go to documents. No, not documents. You can go to downloads. Yeah. And analog flavor eval something. Yeah, you don't need to note this down. It's just you'll find this file. Everyone there? Downloads analog flavor something VAs. Yeah. Yeah. So this has the codes for all 5 models. I just hid this so so no one starts with this. So let's just maybe copy this, take this to documents, Verilog-A, and paste it here, extract, and you'll have 5 files. These 5 files: RL1, RL2, RL3, RL4, RL5. Just get that copy and paste it here. Do you want me to show you that? No, do you want me to show you the copying part, or you can do it? Okay, let me show you. Yeah, yes. It's better if so you found this file? Everyone found this file? Just copy, right click, copy. Go to documents, Verilog-A, and paste. That's it. Done. Open this. Get these 5 files. I don't know if you can do this. Yeah, you can. Just hold shift and select all of them. Everyone able to do that? Able to do that? Yeah. Okay. Select one, select all. Done. Yeah, and then simply drag them and drop them in the EVA folder. Okay. Uh, you pasted the va.zip. Everyone pasted this? Done? Huh? Okay. Downloads. Go to downloads. Analog flavor eval. Yeah, the first one, the first folder. Double click. VAs. Double click. You have a vas.zip. Copy this. Copy. I'm copying this. Okay. Go back to documents. Go back to Verilog-A. Paste this. Okay. Done. Paste it. Open this. Select the first one. Hold shift. Select the last one. Done. Drag and drop. I don't need to do this, but you'll have 5 files in this folder. Done. Yeah, do it. Do replace all, whatever you want. Done. You have 5 files in your folder now. These 5 files. Just yeah. Delete this vs.zip. Delete everything else. You'll have these 5 files, and you'll have compile.sh. That's all you should have in this folder. Okay. Let me start with the first resistor model. What the first resistor model basically is, yesterday we defined modules, right? We defined modules. We defined nodes within modules are called nets. Nodes on the boundary of modules are called ports. Okay? So what we'll be building now is a simple resistor. We'll name it res1. The name of the module will be res1. Okay? and you'll have two ports. When I say ports, which means there'll be two nodes on the boundary of this module. So we'll be having two ports, one port P, one port N. We'll be having two instance parameters, L and W, length and width. We'll be having one module parameter, which is the sheet resistance. Okay. For a simple resistor, the equation would be R is equal to rho L by E, where rho is the resistivity. If it's sheet resistance, then it's rho L by W, right? Because rho is per square, so L and L cancel out, so it's done. Okay. Now we'll see how we build this one. So you can open the first one. Okay. So we have something like this. We have two include statements. The first include statements, the first include statement is about disciplines.vms. This file. See, I talked about these three: define and include. What are these? These are preprocessor directives. Okay. What they do is they simply copy paste stuff. That's all they do. So what this statement will do, it will open this file, this disciplines.vms, and copy and paste everything here in this location, line 10. Before compiling, it will copy and paste everything from disciplines.vms and paste it here. Similarly, this second line will copy and paste everything from constants.vms and paste it here. Simply copy paste. Okay. And then we have a define statement. For define, we said that it assigns something to something. So what it is assigning right now is we have defined this function attr bracket txt. What this means is if it finds attr anyway at any point inside this code, if it finds this attr, what it will do is it will simply replace what is inside the brackets with this thing. You can define a lot of things. For example, it can have more than one argument. You can have, suppose, txt comma maybe abc. Okay, you can have something like this, and then you'll have something like maybe txt plus abc. We'll see an example later. You can do anything with these arguments. No, okay, let me just see. Can you see all these attrs? Yeah, you can see all these attrs now. What this one means is that it will see for this attr call, this part is txt. Okay, this part is txt. Everything within the brackets is txt. Now what it will do is this txt will go. Let me just do this. So what this line means is that wherever you find attr with something in the brackets, replace that with this. Okay, is that clear? So what this line will do is that it will replace this with this. Okay, that's what the attr call will do. You're not required to write this. You can simply write this. This is what is required there. Okay, to make life simple, you don't want to do this at each line. You just define it once, then you make calls all over the place. I'll show you more complex things. It's a very simple, right? It's extremely simple. But you can do many powerful things with this. We'll see one example. We have one of the models uses a very powerful thing to do this. Yes, Yes, this part is basically that txt we defined. Yes. See, this is a placeholder. I can name it anything. I can name it PAC. But then I'll have to do a PAC here too. What this means is if you find ATTR with anything inside the brackets, call that thing PAC. Okay. Then what you have to do is put that PAC in something like this. Oh, is that clear? If you're familiar with functions in C, that's exactly how things work. Although functions are a bit more complex, we'll talk about that. But this is basically it. You just assign it a name. That's all. Okay. So this is what Zeiss requires. You need to define a model group. You need to define a device name. It's exactly the one we saw in when we did MOSFET. When we did a simple SPICE example of a MOSFET, we did this. For example, here, see, what you defined was M1 was a MOSFET with 4 terminals. Then you named it something. Then you called a model statement with the same name, and then you had this NMOS, right? This an equivalent word would be R. You can name it anything. You can name it maybe RES. Okay. For now, I've named it R. And if you see the net list in which we'll use this model, I define R, right? This R and that R are the same. No, this is a separate file. The net list is separate. Okay. This net list is calling a model file. It's calling a model file. The model is R. Like for a MOSFET, it was NMOS. Now, where does that NMOS come from? We want to know where that NMOS is in actual code. Right? That's what I'm showing you. It comes from this. If I name, for example, if I name it NMOS, okay. When I use this model in SPICE, I'll have to write NMOS here. Okay. RES is an instance of it. RES, this name can be anything. Okay, this and this. These two just have to be the same. It can be anything. Let's connect this and this. So, for example, for MOSFETs, we do M1. M is a MOSFET. You name something, the same name you use here. Then you have the name of the model, the type of the model. Yeah. Similar example here, right? Similar example. Nodes, name of the model, instance parameters. Then dot model statement, the same name, the same name. Then type of the model. For MOSFETs, MOSFETs can be NMOS or PMOS. In my case, I just want to call this R. I mean, I can call it anything. Okay, it's just the name. It's a type of the model, and it's up to me to define whatever I want. So, for example, I get back to this R. Okay, then you define a level number. Normally, what level numbers are, they define the complexity of a model. So, if you have a very simple model, that would be level 1. If you have a more complex model, it will be maybe level 2. If you have a very complex model, maybe it's all up to the designer. I mean, it's not hard coded anywhere to write like model 10 should be this, model 11. It's all up to you. It's just for the convenience that simpler models will be lower numbers, complex models will be high numbers. Now, okay, getting back to this. Okay, now P and N, these are ports, but basically all ports are nodes, right? And for nodes, we said we need to define a discipline. For all nodes, we need to define a discipline. For ports, Since they are nodes, we need to define a discipline as well as directionality. Okay. So now getting back to this, since P and N are nodes, we'll be defining discipline. But since P and N are also ports, we'll be defining directionality. You can always have internal nodes. Uh, for example, it's a MOSFET. Okay, a MOSFET can a small single model for a MOSFET would be many capacitors and current sources, right? They will have a lot of internal nodes, but externally, the user just sees three nodes or four nodes, right? DGSD. Internally, there can be a lot of nodes because we have, say, gate resistance, some transconductance, okay? But for the internal nodes, I don't need to define this in out because internal nodes are not ports. Okay. If I had more nodes, I'd just have to define a discipline. But since these two nodes are also ports, I define a directionality. After that we have parameters. So we said we'll have this first model is a very simple model. We have three parameters. Two are instance, one is a model parameter. Again, yesterday we mentioned these parameters can have real values, and they go from 0 to infinity. I can't have negative values for these. And then simply this again, what does this mean? This will simply replace it with bracket star, this statement, this ATTR statement. And type instance says that this is an instance parameter. Yeah, so that's it. Now you also need to define variables for your calculations. Variables make our life easier. I mean, you could have written everything in just one line, but you don't want to do that. It's not legible, you can't read it. Okay? So it's better to do things in various lines, but use variables to store intermediate results. That's common programming practice. You never write everything in one line. Okay? So between begin and end is where comes your model code. This is where you write down all your physics, everything that defines a model. If it's a common resistor, V is equal to IR, oh sorry, R is equal to rho L by A, just write it here. If it's a MOSFET, I is equal to Kp by 2, whatever you want to write. VGS minus VT, just write it here. Everything which defines the model comes here. Okay. So for our first case, which is a simple resistor, we'll have something like R. Now note this R is just a variable, just a holder. We're holding something in it. What are we holding in it? A product of RHOS into L into W. These three values come from the user. When you write a netlist, you give these three values in the netlist, right? When you're doing the SPICE simulation, you enter these three values. So SPICE hands down these three values to the Verilog-A model. So you're getting this. So if you remember this black box, your module, these three values come externally. Now you have these three values. Now what you do is you multiply this to this, divide this, store all of that in a box called R. Nothing more, nothing less. It's just a holder. It's a variable. Now you take that R, invert it, you have another box called conductance. Just a holder, a variable. Okay. Now take this conductance, it has some value, multiply it with a voltage between P and N nodes. Now this is what we call access functions. Yesterday we talked about access functions and contribution statements. So this VPN is an access function. Access functions and contribution statements just work on nodes and branches. You can't use access functions and contribution statements with variables. For variables, you use assignment functions like this, equal to. Don't think of it like it's equal to. It's not equal to. It's not maths. You're in programming, so it's technically it's an assignment function. It's an assignment statement. And again, see this VPN again. The values will come from SPICE. In a SPICE netlist, we'll have defined a voltage source which goes across this resistor, for example. And SPICE will decide what voltage is being applied to this resistor. And that value again comes from spice. So the code knows what this value is. Again, this value is coming from outside. So for our model, these parameters are coming from outside. This VPN is coming from outside. And what are we giving back? So, okay, now I take that VPN, which comes from spice. I get this conductance, which is again derived from parameters which come from spice. I know both of these terms. I just multiply them. I get another variable, again, convenience. No one asked me to do this. You can do whatever way you want. You don't have to do this in another function. You can simply, in another variable, you can simply do this. Instead of storing this in IR and then using IR in the next line, you can simply do this. Simply take it. Yeah? Okay, you don't need this. All of this is just for convenience, just to make it readable. Okay, it's always good practice to store your, for example, you have a numerator and a denominator. You don't want to write everything in brackets and then divide it by then again brackets. It becomes cumbersome to read that. So it's better to take your numerator, store that in something, take your denominator, store that in something, and in the next line take another variable, a1 by a2. Done. Simple. Just to make life easier. That's it. So yeah. Now IR has values, some values. What is that value? It's actually current. So IR is holding the values of current. Now we need to assign that current and give it back to spice. Okay. Now we calculated the current. We know what the current is between the nodes P and A. We need to send that back to spice. That is done through a contribution statement. We can't write IPM equal to IR. IPM is not a variable. Okay, it's an access function. So this is a contribution statement. You take this value in IR, simply give it back to spice. Spice applies a voltage. Now it knows what's the current going through it. Okay. So the IV relation is decided by the model. V is applied by spice. I gets through the Verilog-A model. Okay. That's true for all models. You'll never see I being applied through spice because you can't really apply I. Okay. Whenever you don't have a current source as such, you'll always build a current source using voltage sources. Right? So, okay, so this is a very simple example. And now the next point is using this. So now we built a very simple resistor. That's all you need to do for a very simple model. Now we want to use this model in a circuit simulation. Okay. For example, I made a FinFET in say Silvaco. Okay, and I want to use that FinFET in a circuit. I can obviously do mixed mode. I can simply use that Silvaco TCAD and make a circuit out of it. Maybe it will take 10 days, to run. Because if I have even maybe 10 transistors, it will take quite a long amount of time to do that. It's extremely slow. So what you can do is, if you know how a FinFET works, if you know the equations of a FinFET, you can simply write them down here. Okay. Then what you need to know is these parameters. Okay. And these parameters, how do you get that? Is you take this model, you simulate it. Then you can change these parameters and your simulated results will change, right? For a given L, you'll have something, for a different L, you'll have something else. Then comes what we did before this, IC-cap. We change these parameters, we try to match the output of this model with your TCAD data. Okay. That's what's called parameter extraction. We extract the values of these parameters such that this model behaves exactly like the device we are trying to simulate. Once, okay. Let's say I built a new resistor. Okay, this is the model for my new resistor, and I have the TCAD data for that resistor. Okay, I have the TCAD data. So yes, that's a major data. It's like a real device. Now I know how my resistor works, so I write down these equations. Okay, and I know these parameters. I know these are the parameters. I don't know what are the exact values for these parameters for it to behave exactly like my actual device, right? So what I do is I take that major data, plot it. Then I take my model and I'll plot the output for the same bias conditions. Okay? Maybe the measure data will be like this, the model will be like this. Now I try to tune these parameters such that my model is exactly equal to the measure data. This process is called parameter extraction. So we are extracting the values of these parameters. If anyone has ever used I don't know, mental graphics or cadence, we always use model files, dot .mod, get from the file, right? If you open a model file, it's nothing but the values of these parameters. Has anyone ever tried opening this? It's a list of constants equal to something, right? It's just that TSMC, for example, TSMC, what they do is they measure the transistor. Okay, they measure the transistor. They start IC cap. It's exactly what they do. They start IC cap. They measure the transistor. They use BSIM 3 or BSIM. I guess TSMC uses BSIM 4. They use BSIM 4, and then they use IC cap to fit all that data. When you fit all that data, you get certain values for parameters. It's BSIM is not as simple as this. BSIM has maybe 90 or something parameters. So you can fit this model maybe in 5 minutes because the permutations of parameters is nothing. But to fit a model with 90 parameters, you have so many permutations. As Professor Chauhan said, it takes months. Okay. So I hope you understand where and how things work in the industry. Okay. And how this is going to be helpful. Okay. No, yourself. Because you know your device, right? You know what is the physics of your device. Right? If it's a transistor, yes. Your device might not be a transistor. If it, yes, yes. If it's a simple transistor, if you do some tricks with it, for example, you got two gates, or maybe you give the device such that the physics is not the same as a normal transistor physics, then you need to include that physics in your model, in your code. If it's a normal transistor action, you can simply use any transistor model. Yeah. Let me just show you where you give model parameters. You already saw it. You already saw this in a lot of. So, for example, here, okay, this is a spice netlist. When I say L equals 1 micron, W equals 10 micron, spice takes these values, gives it to BSIM. Okay. So now BSIM receives L is equal to 10. This is equal to this. Does the calculations, gives back the current to spice. That's how you see the IDVG equations. You can do that. You can do that. You can do that. So L, W, you can add. I mean, there's another parameter called AD. You can add that. Whatever you want. Whatever you want. Just go on adding the model values. Yeah, you can define them here. LW. So if you do L equals 1 micron, so actually if you define them down there, it doesn't make a difference. You can define them up, but you can't define model parameters up there. Okay, if you try to do AD equals 1 there, it won't work. You can define all of them down, but you can't define model parameters up. Okay. So this is where Spice takes the values of the parameters, hands them down to Verilog-A. Then Verilog-A does the calculations, sends the output back to Spice. Okay. Any confusions? We have a lot of time, so. No, impossible. Yeah. Yeah. No. Yeah. Yeah. Okay. Yes. If that's what you want. Yeah. You have to change it, then see the output. You again change it, and see the output. Again change it, then see. That's why we don't do that, because that's a headache. If you want to do that, then for this, yes. See, ICCAP is a commercial simulator, and this one is an open source. So you'll see, just adding one device will have to go through a lot of steps. And if you want to do matching, then you'll have to compile it, I don't know, 5,000 times. Compiling it a single time takes maybe 5 minutes if you're fast. So it's definitely not a good idea to do it manually. No, you create a model card using ICCAP. ICCAP is used to create model cards. No, that's not standard model card. You can just enter any values. I guess Raghavendra just showed you copy and paste. That's what you're referring to? That's, you can just have 0, 0, 0, 0, 0. Doesn't matter. The parameter should be specific to the model. See, the model has parameters, right? The model has parameters. This model has parameters. And you tune these parameters so that your IV matches your device. Yeah, okay, let's move to maybe more complex, this one. Let's see how close without saving, close without saving, okay. Now I've written a Verilog-A file, okay, this R underscore L1, everyone has it, don't change it. Okay, everyone has it, R underscore L1.b. Okay, now what we need to do is, now Zeiss is a spice simulator. Zeiss is a spice simulator. So now what we're going to do is, okay, I explained this yesterday. I'll again show you. Yeah, this our plan, okay? This is the plan. Now we have our code. We wrote this. Okay, we just wrote this. Now we'll give this to ADMS. We'll give this to ADMS, and how we do that is, oh, I've written this compile.sh. You can open this up. It simply calls ADMS. That's all it does. So what you'll do is open in terminal. Okay. Everyone there? I'll run this compile running. When I say running, it means dot slash. Okay, dot slash compile.sh. I'll run compile.sh, and as an input, I'll give it r underscore l1.va. Okay, I'm running compile.sh and I'm giving it r underscore l1.va. All this is doing is it's handing over the Verilog-A file to ADMS. That's all it's doing. And the output we should expect is two files. It should give us two files, a C file and a header file. Okay, I'll press enter. Okay, done. We have two files, a C file and a header file. Compile.sh and then the file name r underscore l1.va. Yes, we'll have two files now, a .c file and a .h file. Okay. The plan is to make this device a standard device in Zeiss. Okay, as if it was inbuilt into Zeiss. That's the plan here. Commercial simulators, you don't need to do this. You simply give your Verilog-A code, they'll run it. They work at runtime. Because this is free, because no one cares, you have to compile Zeiss again. And you have to do it such that now Zeiss sees this device as an inbuilt device. Okay, as a default device in Zeiss. So now, in order to get Zeiss to recognize this device as a default device, you have to go through a lot of steps which are boring, and maybe I mentioned something in the slides. If there's something which is not in the slides, you can note that down. Okay. You copy this. You copy this. Go back. Go to this Zeiss 6.10. Open this SRC device modeling PKG ADMS. This location is there in the slides. And do you have the handouts? No, the printed handouts. You can open, if you have your handouts, you can open the page, you can open the slide on which you have those locations. It will be easier. Or you can look at this. It's easier to look at this. Look at this. Just follow this path. Home, documents, Zeiss 610, SRC, device models, PKG, ADMS. It's better to follow this. Whenever you don't know where I am, just look at this. Okay? Everyone there, just paste this. Paste this in this folder. Done? Everyone done with this? Now you'll have to edit the makefile.am. I mentioned this in the slide, but I not mentioned what changes to make. So you can write down the changes you have to make. Open makefile.am. You'll see a lot of cryptic stuff. So you can just see, if you see there are C files, and then in the lower half you have H files. Now you can add a C file wherever you just copy one line of a C file of inclusion of a C statement. Just copy any one line and then paste it, or just add it yourself. You have to add something like this. The name of the C file you just pasted, and the name of the C file is simply n_dev_adms res1.c. Make sure you don't have any space after this backslash. This is important. Make sure you don't have any space after this backslash. After. There should be nothing after this backslash. And why is that important? We'll talk about it when we discuss macros. There should be nothing after this backslash. The easiest way is simply copy one of the lines. Simply just copy this, press enter, paste, and then edit this name. Everything after ADMS and the dot. Just say res1. Okay? That's the easiest way. You won't make any errors. If you do it manually, you definitely make some errors. Simply copy one of the lines, change the name of the model at the end. Okay? Similarly, towards the end, you can add one line which says res1.h. But make sure you do it somewhere up, not in the last line. Okay? The last line should not have a backslash. You just leave the last line, do it anyway up about that. Sorry? Yeah, I'm saying you just do it anywhere but the last line. Okay, done? Yes, the name is same, just .h. Done? Everyone? Now you go to this n_dev_register adms device.c. Everyone can find this? n_dev, it should be the second last file. Yeah? Everyone there? Okay. Open this up. See a lot of header files. Include one more header file, the one you just copied. Include the header file you copied from ADMS. Include this header file you got from ADMS. Done? Okay. Then add one line at the end. Just copy one of these, paste it at the end instead of this HIC. For example, just copy this ADMS HIC0 full, paste it at the end, replace HIC0 full with RES1. Everyone done? Yeah. Yes. Before that, include the header file you just copied, n underscore dev underscore ADMS res1.h. You have to go through all of this headache just because it's open source. You can also use ngSpice, but the procedure to include a model is even more complex, so this one's much simpler. Done? Should I move on? Okay. So now after this is done, now you go back to the Zeiss 6.1.6.10, this folder, Zeiss 6.10. Get back to this folder, right click, open in terminal. Zeiss 6.10. This one, Zeiss 6.10. Open in terminal. Right click, open in terminal. Everyone there? Just say /bootstrap.sh. I guess this line is there on the slide. And press enter. Oh, what happened? Oh, okay. Yeah, not dot sh, just bootstrap. /bootstrap. Done. Anyone having any problem with this? No? Okay. So now get back to documents. Enter Zeiss build. Right click, open in terminal. Zeiss build. Open in terminal and run compile.sh. Again, when I say run /compile.sh. Okay. Let it wait for some time. Let it do some stuff. And this step might take some time depending on your PC. Now everything after this will be easy because I've named all the modules res1. So you don't have to copy and paste the file again. You just have to copy and paste the file again. You don't really have to edit those make file and C file. So those two steps will be saved for the rest of modules. Okay, now once this is done on every PC. Okay, Then you say make. That's all. Make, enter. See, now it's reading those files. See, res1.lo. So it's compiling them. Now it's taking those model files and including them in Zeiss. Now they'll behave as if they are normal Zeiss devices, a normal resistor in Zeiss, with the model number 10, with the level number 10. A normal resistor in Zeiss with level 10. Okay, done, everyone. Next, you do a sudo make install. Now you are reinstalling Zeiss. You just recompile the Zeiss. Now you are reinstalling Zeiss. You'll need your password, which is nanolab at IIT. Okay, done. Now our model is part of Zeiss. Now it's a standard device in Zeiss. Now you can use it anywhere. If you write a netlist, you can write a netlist anywhere. Just for uniformity, I made a folder, this netlist folder. Just enter netlist, sudo make install. Again, nanolab at IIT. Once this model is part of Zeiss, your next step is to simply write a spice netlist and call a resistor with level 10. Okay, that's all you need to do. When you're calling level 10, it will automatically know that it's your, yeah, it will automatically know it's your model, because that's what we mentioned in the Verilog-A code. So you can just, I guess this one is there on your laptops as well, circuit.save. Yeah. So it's a very simple netlist. We have a voltage source between ground and node 1 with the 1 volt. Then we have a resistor R1 between node 1 and ground. Okay. And we are using a model with the name res. The instance parameters are 1, L is 1 micron, width is 3 microns. Okay. And your model file is, again, for this res name, your model is R. We all remember where this R came from. Your level is 10, not 11. You define a sheet resistance. Since these parameters don't exist, it will simply ignore them. You can leave them here. Okay. Since these don't exist in the Verilog-A code, we simply ignore them. Okay. You don't need to care about those. We'll be using these parameters for higher models. Okay. Just keep it there. We'll use the same netlist. Then what we're trying to do is we're trying to sweep. I guess, yeah, it will be okay. Let me do a simpler one. Just take all of this, copy this, copy it, everyone, copy, double click here, double click on the free space. You'll have a new file, you'll have a new tab. Okay, paste. Okay, and save. After copy, okay, double click here in the gray space. Okay, yeah, or do file new. That's all. Then paste it, then save, Control S. Okay, let's call this new netlist. Let's call this L1.cir. Okay, whatever you want. Let's all do capital L1. It's not required. You can name it anything. Okay, done. Save it. Now this is L1.cir. Just, yeah. Now level is 10. RHOS is needed. Just delete everything after this. Keep it like this. Remove the temp part from the DC statement. Done, everyone? I guess it's star again, that block comments, because this is, or is it, I guess it's hash for spice. This is not Verilog-A. This this is not Verilog-A. It's a spice netlist. You don't confuse Verilog-A with spice. Spice uses Verilog-A models. We are using our model. Okay. Now we have a DC statement with V1 going from 1 to 100 in a step of 1. We'll be measuring V at 1 and I through R1. Okay. Just save this, and then now you have your netlist. You have your code, you included that model in Zeiss, you have a netlist. Now just simply call Zeiss and provide this netlist to Zeiss. That's all you need to do now. Open in terminal in this folder, call Zeiss. Zeiss, simply write Zeiss, X capital, Zeiss, and then the netlist, L1.cir. Oh, in what? You did something wrong? What? Line number 4. Okay, let me try. L1.cir. Yeah, it's running perfectly. Hmm? Make. अभी make पे ही हो. Make तो बहुत पहले हुआ. sudo make install. sudo space make space install. हाँ, nanolab at IIT. Okay. Now we have spice. Now we have a spice simulation done. You use this model. We have a spice simulation, and you'll find this l1.cir.prn. This is the output file now. All you need to do is plot this. Again, open in terminal, run plot.sh by run again dot slash plot.sh, and you run l1.cir.prn. Okay. Here's an easier way, just press tab, it auto completes. In Linux, you press tab, it auto completes. Double click on this one, l1.cir. Double click. You have a register model, right? Huh? Dot slash plot.sh followed by the name of your output file, the PRN file. Okay, a simple register. Let's change a parameter and see what happens. Okay, let's change a parameter and see what happens. Can you guys read the current? Okay, let me see. The current at this point, at 100 volts, the current is 599.8 amperes. Okay, blank, blank or black. Yeah, just double click on that. Double click on L1CIR.PRN. Okay. Yeah. At 100 volts, I see a current of 598.699. Okay. Now let's use common sense. If I increase the width of the resistor, what will happen? The current at 100 volts would be higher or lesser than this? Higher than this. The resistor is going down. The resistance is going down, right? The current should be higher than this. Let's do that. Now what I'll do is I'll simply change this L1.CIR. I passed a width of 3 microns. Let me pass a width of 6 microns. Okay, I can do that. Save this file, run Zeiss again, Zeiss L1.CIR, enter. Then now you'll have the PRN file, then plot.sh L1.CIR.PRN. Let's see. Yes, obviously. The current is now 1.19 K, 1000. Makes sense, right? We doubled the width, the current is double. Okay, so the model is working. A very basic model is working. Let's go on and do something different now. Let's change, let's make a more advanced model. So the one we saw was a very simple model, right? Resistors can't be that simple in actual life. Now, if you actually make a resistor on a wafer, you will make two contacts. You'll have something in between, right? That's a resistor, right? If you make a simple resistor on a wafer, for example, this is my resistor on a wafer. I make these two contacts. Does everyone agree that the currents won't just move from this end to this end straight, right? There'll always be currents which take a longer path. Make sense? Right? You can't stop currents from going this way because there'll always be a field which will be going through that route, right? So there'll always be currents which will be going through this route. Okay? So you can't say the effective length is actually L. Some current paths see a longer length as compared to some other current paths. Some current paths see a shorter length, some current paths see a longer length, right? Okay, if the width of the resistor is small, if you have a very wide resistor, if this is very wide, you'll have a lot of parallel lines, right? And a very small number of these lines. So you can simply ignore them. But if your width is not that much, if your width is not large enough, then it's something which is similar to charge sharing in MOSFETs, right? If you have a very wide transistor, or if you have a very long transistor, you don't really care about charge sharing. When you go on decreasing, then your depletion charges start playing some role, right? So it's exactly the same. So there's a width dependence, there's a length dependence. Now, if you have a length, now let's see at the resistor through a cross section. You have these contacts. Now this was the top view. You can also have a side view, a cross section. You have these contacts, right? And you have current paths which go deep inside, which are longer. These current paths are much longer. And these depend on the length. So you have both a width dependence and a length dependence. So the actual length you define in the mask is not exactly the length which the resistor sees. So how we model that, you can go to this book called Compact Modeling by Gennady Galgenblatt. It's a standard book for compact modeling. You'll see a lot of models for resistors. I just covered two or three simple models. These are still not physics based. These are empirical models. They are just common sense models, right? We don't talk about any Gaussian equation or anything. This is simple empirical calculations. So length, the actual length of the resistor would be the length we define on the mask, okay, plus some delta length, because your mask and your actual fabricated device are definitely not exactly the same, right? You'll have some deviations. And then there is there's some deviation due to width, just like we said. Due to width, there's the length of the resistor changes due to width, which is the effective length actually. This L is the effective length. So this is one equation for the actual length of the transistor. The width is actually much more complex. See, if this is how a resistor looks like when you actually fabricate it. You have a lot of contacts, you have some body, maybe polysilicon or whatever you want. Then you make some of these contacts. You have like a broader region at the end, a narrower region in the center, like a dog bone. It's called a dog bone structure. Okay, this is how resistors are actually fabricated. The width dependence is actually much more complex. Okay, length dependence is quite simple because the effects are simple. Width, you can have, if you're, see, you can never have such a sharp turn, right? You always have, you can't fabricate a sharp cut like this. You always be smooth. That gives rise to this exponential dependence. And less the lesser this ln is, the more pronounced these effects will be. So you'll see a lot of effects. Some effects depend on Wn. For example, this delta WW is change in width because of width. Okay, so it depends, and then you have change in width because of this WFD. This WFD. Uh, I guess it's this one. Okay, if I remember correctly, was no WWE is the webbing. This is called webbing effect. Okay, and WD is what? WD is this this extra part. So if WD is more, you have more webbing effect. So what I want to say is, even something simple like width can have a very complex dependence on other geometrical parameters, right? Similarly, now what you can say is the total resistance would be two times, because you have on both ends the resistance of a contact divided by number of contacts, which makes sense. If you have more number of contacts, your resistance should be less, right? Because you have more paths for the current to flow. And if your resistance per contact is more, then you should have more resistance. And similarly, what you can define is this REW is this entire resistor, and then divided by Wn. So yes, so now this REW by Wn is basically just the resistance of this region. It's a Wn. Okay, and then you add all of this to your actual resistance, which is rho L by W. Rho S, this was the simplest model we made in the first statement. Now we have a huge geometrical dependence. This is where I want to mention something which I mentioned yesterday, the limits on parameters. For example, you have this thing, 1 minus exp minus Wm by Wft. Now Wft is a parameter which the user gives us, okay, and he can enter anything. You don't want WFD to be 0. So it's your job to ensure that WFD does not go to 0. Okay. And this exp function, right? This exp function, normally what happens is exp functions, they grow quite quickly, right? So there's a precision limit to computers. You can't go beyond a certain precision. So if you have e raised to power 80, for example, if you try, I guess Professor Chauhan mentioned expx minus expx plus x minus expx, right? If x is too large, it should show you x, but it will show you 0, right? If I do so, if you write something like exponential of x plus x minus exponential of x, by simple algebra, I should say this should be equal to x, because exponential x cancel out. But because computers are limited in precision, if x is too large, okay, it can't. So exponential of x is a huge number, okay, and x is a very small number itself. For example, 80. 80 is a typical limit for computers. E to the power 80 is almost the highest number a computer can store. Anything higher than that, it can't store it. So what we do is we always limit exponentials. In all compact models, you'll see exponentials are limited. You define a maximum number. Any argument which is passed to this exponential is limited to say 80 or something like that. We'll see it in the next example. So if we can open the other file, you can open the L2. Now we defined a max arg of 80. Okay. A max arg of 80. And the reason we do this is because we want to limit exponentials. We don't want exponentials to grow after this, because that would cause computational problems. So what we do is, it's the exact same module, okay, same electrical, again a two-terminal device, in out. Now this is another it's a function. It's how you define functions in Verilog-A. Functions can be used, like in C, you can do a lot of things with functions. Function they can take in arguments, they can give out some values. So what this function is, whenever we want to use an exponential, we won't simply write an exponential. We'll write this function. And what this function will do is, if the exponential argument is higher than max arg, okay, so it will simply replace that with a linear line. So what it will look like is, maybe I can just show. This is what we're trying to do. If you have, this is your exponential, right? This is how it goes. If your x goes beyond 80, okay, it will start, instead of growing like a vertical line, almost a vertical line, it will start growing like a linear line, like this. Now you might say this is going to affect our accuracy, but we don't really care about accuracy at these numbers. And you will never reach these numbers if it were not for Newton-Raphson. Okay? Actual physics will never get to these numbers, but Newton-Raphson takes it to these numbers. Yeah, we saw the examples, right? You take guesses, and the next guess could be anywhere, right? You'll never have in a device. You'll never have something raised for 80. It's impossible. This is to ensure that if Newton-Raphson does take it to that point, there should not be convergence problems. Okay, so you limit this to 80. After that, it rises like a linear curve. So in order to do that, what we do is, yeah, like this. You define a new function for exponentials. Whenever you want to use exponentials, we'll use this function. Okay, and we define the input. This function will take one input. That is the argument. If I have to do exponential of 3, I write expl bracket 3. So just one input. This is a single input function. I can have multiple inputs. I can have x, comma, y, comma, whatever I want. Then this input has to be real. It cannot be an integer. I mean, it can be an integer, but if I wrote integer x, it could not be a real number. And then what to do with this input? You take this x, and just like modules had, the analog block had analog begin and end. Functions, analog functions also have a begin and end. And between this begin and end, you have your mathematics. Okay, so if the argument which is passed to the exponential function is less than max arc. Okay, this means we are calling max arc. Max arc is defined as 80, right? In the line above, max arc is defined as 80. If the argument to the exponential function is less than 80, then the output is the same as exp of x. So if it's less than 80, you're simply passing out exponential of x. If it's not, then expl, see this expl, it's the return value. It's something which is sent back. This expl is this. What this means basically is it makes a straight line after the max arc point, if you do the maths, right? It's exp of 80 into a straight line. So it's like y is equal to mx plus c, but you start from that exp 80 point and then you draw a straight line. So the purpose of this was basically to show you how functions are defined in Verilog-A. You can do many more, you can do complex functions if you want. For example, you want to calculate the threshold voltage. Okay, and threshold voltage takes in say five parameters or 5 variables. You can write a function for threshold voltage, and wherever you want to calculate threshold voltage, you can simply call that function. Okay. Now, as we saw the example, we had a lot of parameters, right? We saw a lot of parameters. Some parameters like this, del L can be 0. No harm in keeping it 0, right? Nothing will blow up if del L is 0. So you can include a 0 in this. Okay. What this means is it is 0 with 0 included. Similarly, NC, number of contacts. A resistor will always have 2 contacts, right? You can't have just one contact and the other end is loose. So number of contacts will always start from 2. So this is how you set limits upon the user. If the user enters NC equals 1, Spice will throw an error saying parameter out of bounds. I don't know if anyone has encountered this error before. Parameter out of bounds. You'll get a parameter out of bounds if the Spice gets a value out of this range. So these are the default values. You can set anything you want. Yeah, these equal to. So you're assigning something. This is default. Yeah, you can. I mean, normally what people do is, normally when we make a model, we assign parameters in which everything is within bounds. Like if we do a MOSFET model, we set the parameters such that your S parameters are within bounds, your IV curves are within bounds. Okay, nothing is very exotic. You don't see crazy S parameters. Everything should be normal, looking normal. That's all. Okay, now, as I said, if you have say a numerator and a denominator, it makes sense to assign the numerator to a variable, assign the denominator to a variable, and then simply do A by B, right? So if we look at, let me just put them side by side. Can you see these? So width W, I call this width effective in my code, is something divided by something, right? So I take the top something and I take the bottom something. So the bottom something I've written T2. T2 is 1 minus WE, which is a parameter, which the user gives us. WD, which is again a parameter, which the user gives us. LM, again a parameter, which the user gives us. WM, again a parameter which the user gives us. Okay, so this entire thing I've saved in T2. The one above, I've divided into two parts. There's delta WFD into something. This into something I've taken out. So T0 is this part. 1 minus exponential of minus WM by WFD. But instead of using a normal exponential, now I'm using the one I defined earlier, this EXPL, right? That's just to ensure that things stay in limit. That if the Newton-Raphson algorithm takes things too far, nothing breaks down. Okay, and then I simply add this T naught to the rest of the equation. So after this, it's basically just algebra, nothing else. You won't find anything new. Yeah, the entire purpose of this one was to introduce you to, one was this parameter bounds, the other one was limiting exponentials and also functions, how to define functions. I don't think there's a need to simulate this one because the resistor behavior will almost be the same. You won't find any big difference. Okay. Okay, let's go to the third model. Yeah, this one's interesting now. Okay, remember we talked about, okay, not yet. Okay. Spice can also hand down temperature information to the module. Okay. You can also vary temperature in Spice. If you do a DC simulation, you can also write, I guess you just saw that in one of the netlists. If you open circuit.cir, in a DC statement, you can also write temp, right? So Spice can tell the model that the temperature is varying from this to this. Now, how does the model know what to read? Okay, so Verilog-A has a special uh, keyword. It's called $temp. This one, sorry, $temperature. Okay, the value of $temperature comes from Spice. Again, not parameters. Whatever you mention in a DC statement in Spice comes down into this variable there. It's a standard variable, you can't change it. Whenever you want to know what temperature is being sent from Spice, this is what you use. $temperature. Okay. Okay, for this one, let's move to the next model I have. Okay. Yes. So till now we had the geometric dependence of resistors. Now we want to see temperature dependence of resistors. So temperature dependence, what you do is, you say temperature, resistance as a function of temperature is equal to resistance at some temperature at which I did a measurement, okay, which we'll call a reference temperature. Okay, suppose 25 room temperature, for example. So resistance at any other temperature is equal to resistance at a reference temperature into 1 plus a parameter Tc1 into delta T. Delta T is difference in temperatures. So how far this new temperature is from the reference temperature. So this is like a linear temperature dependence. Okay. And you also have a quadratic temperature dependence. You can also have a cubic temperature dependence. Depends on what you want to model. Remember, all of this is just empirical modeling, no physics. In an actual physical model, the temperature would come in kT. If I had an actual diode model or an actual resistor model, I'd have it in somewhere in the Fermi equation, in the Boltzmann equation. The T would be the T in kT. Everywhere where you see a kT, you would see some temperature dependence, right? So all of this is just empirical. We're trying to model some sort of temperature dependence. So, and this is a good first fit. I mean, you can make a simple model out of this. So this TC1 controls the linear temperature dependence. TC2 controls the second order temperature dependence. And delta T is T minus T ref. Okay, this T is the temperature at which the device is. This T comes from spice. Okay, T ref is at which you did the measurements, or at which you know what the behavior of the resistor is like. Okay, so now what you can do is the temperature dependence can be for the body as well as for the contact region, because the contact region is a different material, right? We this the resistor body is made of a different material. The contact region is made of a different material. There are different temperature dependencies, right? So you can do that here. This REWC is actually the resistance of the extra region. This rho L by W is the actual resistor. So you can have temperature parameters for the extra region E and temperature parameters for the body of the resistor B. So TC1E is the temperature control parameters for the extra region. TC1B is the temperature control parameter for the body region. So for example, I want to do something like this. And if you rearrange all of this, you take, you define this, this RT, and you manipulate here and there, you'll get something like this. Okay, 1 plus some parameters into delta T, something into delta T squared. Okay, now again, here's where you need to keep, you need to think differently here. What you would normally do is you'll write in your code, you'll write 1 plus da 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 into delta T plus da 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 into delta T squared. Delta T is what? Delta T is T minus T ref. When you do a square, you have three options of doing a square. You have basically two options. You can either do delta T into delta T, right? Or you can invoke what's called a POW function, a power function. You can say POW delta T comma 2. Raise delta T to the power of 2. Which one do you think is good? Which one do you think should be done? Okay. Here's where you need to think. See, functions. Do you know how functions work in C? Functions. When you call a function, I don't know, for assembly maybe you know. When you call a function, you you create what's called a start frame. You call a function, the processor reserves a different memory space, and it starts building a memory space in that region. Then when it returns, it takes that, comes back to the original location. I hope you remember something of that sort, right? You call a different memory address. All of that is extremely slow. Memory operations are extremely slow. Okay. What if you try to do delta t into delta t? All of that just goes to the ALU, right? No memory, simply ALU, and ALU is very fast. Okay, so choosing POW delta t into 2 is the worst decision you can make. Okay, even if you do delta t into delta t, that's also like very complicated. So you can even make it simpler. There's something called Horner's rule. Okay, let's do this. Let's okay. If I have something like this, a naught plus a1 times x plus a2 times x squared plus a3 times x cubed, right? I can do something like this. You read this. You'll find it eventually evaluates to this one, right? But you'll need much lower number of registers to store the data. You come from the internal block, you go on adding. Okay, you don't have to store two x's, right? At any point, you don't have to store two x's. X is stored just once, and then it's used again and again. Okay, so all this is important when the code is quite long. When you have an actual MOSFET model, you don't want to spend even 1 or 2 minutes on a single device. In a processor, you have like 1 billion transistors. Right? In a large circuit, you have say 100, 200 transistors. If you spend 1 minute on one device, you're spending 200 to 300 minutes on simulating the circuit. Okay, even these small things count at that level. You want to make your model as fast as possible. But this might not be important for novel devices or for research, but when it goes to the industry, these things matter a lot. Okay. Okay, let's see how we do this in the code. Okay, so this is delta T, the temperature we get from the spice, and Tref, which is again a parameter. Okay, I know I did a measurement at 25 degrees Celsius, and I extracted all the other parameters at 25 degrees Celsius. Okay, then Tref would be 25 degrees. All the other parameters would be what they are. That's all I need to do. Okay, Tref is the temperature at which all the parameters have been extracted. Okay, it's normally in Kelvin. Okay, so that's why if you go back to this, set from 100 Kelvin to 500 Kelvin. Okay. But you can always do Celsius. You just have to write one line above which converts that to Celsius. That's easy. So for example, you want your user to enter Celsius, you'll take that parameter, maybe do 9 by 5 or whatever we do. No, that's for Fahrenheit. Okay, add 273 to it. Yeah, that's it. Okay. Again, after this, see, I used a very inefficient way of doing the square, right? I used this POW function. Yeah, it's better to use that honest rule to make it more efficient. But efficiency in this case doesn't matter because the code is quite simple. Now let's simulate this one because you can see the temperature dependence. So let's go back to documents. Verilog-A. This one was R underscore L3, right? So we'll do open in terminal. We'll do compile dot sh R underscore L3. Done. Okay. Okay. From these equations, what do you think will happen? From these equations, what do you think will happen if the temperature increases? The resistance will go up, right? That's what we see from these equations. That's all up to you. If you mention TC1 to be a negative parameter, it can even go down. That all depends on how the measured data is behaving. It can behave in any way. So for now, for the equation we've written, an increase in temperature means an increase in resistance, which should show us a decrease in current. Let's see if we get that. Now we have these two files, C and H file. We simply need to copy this. What happened? Copy this, paste in SRC device model PKG ADMS, yeah, paste and replace. Simply replace both of them. Then you don't need to do anything in this folder anymore because the name is the same, right? Just go back to Zeiss 610. Again, the same steps. Open in terminal, bootstrap. Bootstrap is done. Get back Zeiss build and compile.sh. Sorry? Yeah, that's after this. And by the way, till this happens, move ahead. We'll see the results of this one. Till then, we'll discuss. Now, we saw macros. We defined macros, right? We define macros, and macros are basically, they are supposed to be just one line. Okay, but we can also define functions in macros. If you have an entire function in one line, you won't be able to read what the function is doing because you have to see, you have some if statements, some in statements. I mean, you can't really understand what's going on. So in order to make it legible, we try to make it in multiple lines. So that we say, okay, this is a variable going on, and then we have an if statement, we have something else. We want to make it into multiple lines. But basically, macros are just single lines of code. They have to be just one line. You say define something, after that, it should be just one line. It can't be an entering. And how many of you know what new line characters are? New line characters, anyone? No? Yeah, backslash n. You can't really see that character, but it's always there, okay? When you press an enter, what your processor or what your word processor or even PowerPoint does is, it enters that character there. You can't see it, but it behaves as a new line. Let me just show you how it works, just in PowerPoint. If you, for example, if I select this one, okay, this line I selected, I can also do something like, can also select it up to this, see? Okay, there's no difference between selecting this and this, apparently. There's no difference, right? It should be the same. Let me show you what will happen. So for example, if I copy just this part without the extra space, although there's no space there, if I click here, I won't be, if there was a space, and I would click at the end of the line, it would, the blinking would be at the end of the space. But there's no space there, right? But you can still select one character ahead of E, although there is no space there, okay? Now, if I don't select that part and I copy this and I paste this in the next line, just that is copied, right? Now see what happens if I copy this. I'll do the same thing, but I'll also include that extra space, which is actually the new line character. Now I'll copy the entire thing, okay? Now I'll copy the entire thing. Now same thing. What happened? Okay, you automatically got to the new line. Although the new line character, you can't see it, and you can't even select, I mean, you can't really access it, but it's always there, okay? And in Linux, You remember I said when you edit that file, there should be no space after that backslash. That's the reason. If you enter a space after the backslash, the new line character enters after the space. Okay? And what happens is that entire thing, which was supposed to be a single line, now becomes two lines. Okay? So let me just build this. Yeah, so, okay. Yeah. So new line, you have to escape it. And you escape it by using a backslash. Okay. So if I had to write something in a single line and I press enter, but at the end of that first line, I enter a backslash. Backslash is an escape character. You even use this in latex, right? I guess for dollars, you can't write a dollar without a backslash. Otherwise, it will take that as an equation. So backslash is called an escape character. And if you have a backslash at the end of a line, it means you're escaping the new line character. So new line will not be validated. But if you have a backslash followed by space, you'll be escaping that space and not the new line character. Okay. In that case, the new line character acts and the line it breaks into two. So you have to ensure if you are making a multiple line macro, you'll have to ensure that the backslash doesn't have anything following it. Guess it's done. So we'll see one example. See, before this, what we did was we implemented the exponential function as an analog function, right? Again, the efficiency factor comes in. When you define functions, as I said, a function call is again, you call a different memory location, right? Like POV is for two. It calls a different memory location. And when it builds a stack frame, after the processing is finished, it comes back. Slow process. Remember what macros do. Simply copy paste before even compiling, right? So if you write a function as a macro, it's much faster than writing an analog function. Okay. You see, if you see our model, this ASM, all these surface potential equations, okay, surface potential calculations, they've been done as macros, not as functions. Yeah, like maybe 50 lines of code, surface potential equations. You won't do them in analog functions, or your code will be extremely slow. You do them as macros. And for macros, in order to understand them, you have to escape the new lines so that you make the multiple line. I'll just show you. Yeah, before that, let's see the previous example of the temperature dependence. So it's already built. So we'll go back to the netlist. Now we can use this one, circuit.cir. Okay. Now we're simply taking the temperature from 100 to 500 with the step of 50. The same 1 to 100. Okay. I'll simply build this now. Open in terminal. I'll do Zeiss circuit.cir. And I'll do plot. I don't know if you can see this. Wait. Yeah, you can go down. There are many other lines. Okay. So these are the different temp. Now this was the secondary sweep, right? Temp was at the end, VG was at front. So the primary sweep is VG. The secondary sweep is temperature. So this is VG, not VG, but V sweep for different temperatures. And you can see the resistance comes, or it actually goes up. I don't know. Run 4, yeah. Run 3. No, not really defined it. Anyway, it's changing with temperatures. Let's not dwell into details. So it's changing with temperature. The last thing I want you to see is self-heating. Okay, we defined it yesterday. Now, what is self-heating? Once current starts flowing through your device, it starts heating up. So your temperature goes up. Now your temperature goes up, uh, then your resistance increases. So your currents go down. So if there's self-heating in the device, I should see something like this, right? If there's self-heating in the device, as the currents go up, its resistance should increase and the current should decrease. So it should make something like this, right? That should be a self-heating behavior. That's true for MOSFETs, that's true for resistors, anything which is fabricated on a structure. But last, self-heating, self-heating. Okay, so this would be the last example, and now how to model self-heating. If you remember, we defined many disciplines, right? We defined the electrical discipline, we defined the thermal discipline. And inside a module, you can have nodes which belong to both disciplines. Yeah. Yeah. Let me just simplify. So earlier we had two nodes which were also ports, right? P and N. They were ports and nodes. Now we have these two which are defined as electrical nodes as well as ports. So they have a directionality, they have a discipline. Now we also define something called thermal node. So this TE is a node which has a discipline of thermal. We saw disciplines, there was a thermal discipline. And thermal discipline had a potential of, does anyone remember? The potential in a thermal discipline was temperature. And the flow was, no, not heat, power, right? The flow was power. Flow was power, the potential was temperature. Like in electrical discipline, the potential is voltage, the flow is current. So what we define is, again, we said branches, right? So branches, so now we have this TE node inside, which is defined by the thermal discipline. So if I do an access function on TE, if I do a temperature access function now, not a voltage access function, right? TE has a temperature, not a voltage. I'll do a temperature access function on TE, that will give me the temperature of TE. If I do a power access function of between TE and some other thermal node, I'll have the flow of power between TE and that node. Okay. Now what we do is, when we define a branch with just one node, it automatically defines another ground node. Okay. So when I say branch TE is equal to RTH, it means from TE to a ground node which is thermal, which is also thermal. Okay. There exists a branch RTH like this. This is what happens when you define these two lines. It makes two branches. One is RTH from TE to ground, to some thermal ground, and from TE to ground there's another branch called ITH. Okay. Then, then the temperature of the device is the temperature which it receives from SPICE plus the temperature of this node TE. That's how we define it for self-heat. So what you can say is, to start with, this should be 0. Right? Now all you have to do is make this thing current dependent. The more current you have, the temperature of RTH should go up. That's what you need to do. If the temperature of RTH goes up, it adds to this main temperature and the temperature of your device goes up. Right? We use this TRES, we use T in T minus T, T minus T ref, right? Now instead of T minus T ref, we'll do this thing minus T ref. Okay. So now this PWR, power. Now the flow is power, it's not current. Think of it in similar terms. Current is power for thermal nodes, voltage is temperature for thermal nodes. Okay. PWR ITH, the current, the thermal current which is flowing through ITH is equal to IR is the actual current which is flowing. V, so this is the power, right? V into I. Right? The more power which is being generated by the device, the more current is flowing in this ITH branch. If more current flows, then voltage changes, right? In electrical discipline. In thermal discipline, what would happen? Temperature changes. Okay. Exactly the same. Just think of voltage like temperature, current like power. That's all. Then PWR of RTH, that is the current flowing current. When I say current, I mean thermal current, not the actual electrical current. The thermal current flowing through RTH is, see, this current is going out, it's minus. It's like current is going out, current is coming. This current is positive, right? So what is this? It's like voltage on RTH, right? Temp on RTH means it's a potential access function for thermal nodes. Temp. Temp on RTH divided by RTH naught. RTH naught is a parameter we define. Take this RTH naught on the other side. Think of it like this. V is equal to IR. Okay. I is equal to V by R. See, this is V for thermal nodes. Temp is the potential for thermal nodes. So this thing is called a thermal resistance now. Okay. The more thermal resistance, if RTH naught is large, okay, just take it on the other side. If RTH naught is large, now this a single current would flow through this, right? If RTH and if your current goes up, the current from this node to this node increases, which means the current from this node to this node automatically increases because it's a single path. What would happen is if PWR RTH increases because PWR RTH increases because it's a single loop, and multiply that with RTH naught. Take this RTH naught on the other side. What would happen is temp RTH would increase. It has to satisfy that, right? Simple VI relation. I is equal to something. When you say I in this branch is flowing, and this I increases. If this I increases, which means this I also increases because it's a single loop. If this I increases, that is this increases, this you take it on the other side, multiplies to that, and the temperature of RTH increases. Right? Now we also said that at higher frequencies we want to bypass this. So that's another thing. You can do C dV by dt. Right? I is equal to C dV by dt. Exactly the same thing. C dV. Now potential for thermal nodes is temperature. dV by dt. The same thing. Let's just see this in action and we'll end this. Now we have the last one. Okay, yeah. See now okay, I didn't take the exponential function. I took the V effective function. I took V effective, and instead of defining it inside, I defined it through a macro outside. Okay, this is how you define a macro outside. See, there's nothing behind this backslash. There's a space between this and this, but there's nothing behind the backslash. There's nothing behind. There's nothing behind. There's nothing behind. Okay, all of this is a single line. This is how you define a function in a macro. This function is going to take in all these values, okay, and it's simply going to give out this. You have to define all of this in one line. And then when you have to call this function, so you simply do this. What this will do is simply paste all of that. Much more efficient. Okay. Okay, now we define, as I said, thermal node TE, then two branches. Standard practice for any device. If you want to do so self-heating, standard practice. It's applicable to any device. Go down and instead of temperature, you have temperature. So I could call this T dev maybe. You'll see many codes calling it T dev. key device. It is the actual temperature you get from SPICE plus the temperature of the RTH node. And the temperature of the RTH node you change by these equations based on the current which is flowing through the resistor. Let's quickly simulate this and we can head out for dinner. Okay, so again, the same steps, compile.sh r underscore l5.va, go to, oh, sorry. Replace these two, get back. Oh. I hope everyone got an idea of how things connect to each other, right? From device measurements to circuit simulations. Ready? पूरा ready? बाहर पूरा ready? Hmm? Huh? Okay, now we can simply use this. Quickly, Zeiss circuit. Can you see this now? So if I go to the lowest one, yeah, notice the difference. Uh, these are high currents, right? High currents mean high self-heating, right? So you see a much more prominent decrease in current. Low values of current, you don't see much because the temperature is not increasing much. So yeah, that's all. Done. Done, 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 done. That's it, done. Done, done, done. That's it. Yes. Aishan?